to have you with us tonight for our discussion on extrasolar planets. Very fascinating topic. Got lots of good information to share with you. Generally, we go between 60 to 90 minutes or so, and then I'll be glad to take any questions that you might have saved up by that time. Okay, so again, pleasure to have you all with tonight. Quite a topic, as I said. A topic that we've wondered about for centuries, people have. And by now you probably know that we are well aware of other planets around other stars. And to me, it's such an amazing field of astronomy that we can learn so much about these planets, as you're going to see, and compare that to our planetary system. And often we're going to find out a lot of information about these planets without ever seeing them. So to me, it's just quite remarkable how far we've come. So let's start out with some of the basics. How do we know? How would we find other planets around other stars? Well, really two main ways, kind of the direct method, so to speak. Let's take a picture. Or more of an indirect method, as we're going to see here in a few minutes. Now, as you can see, there's quite a difficulty to the direct method. Picture, for example, how bright a star is, you know how bright our sun is, and really how faint a planet would be. When we look at our very own solar system out towards Pluto and beyond, the objects are extraordinarily faint. Well, imagine now looking many, many times farther around another star to try to see planets. It's extraordinarily difficult for us to be able to do that. And in fact, only very recently have we even been able to do that. But in contrast, I'm going to talk for a few minutes about indirect methods of finding planets, where we don't necessarily see the planet, but we have solid evidence of its existence. So let's go ahead and do that. We're going to look at two different ways to find a planet indirectly. And the first one has to do with gravitational tugs. I'm going to share a couple of little animations to illustrate this, but the idea here is if we have a star and a planet going around it, many of you already know that when we think of the star as being fixed and the planet circling around, it's not quite 100% accurate. The star moves very slightly as well. So let me illustrate what I mean by that by sharing this little animation. Technically, we describe that by saying, well, it's the center of mass. So here we have a star and a planet, and as the planet is moving around the star, notice if you look carefully that the star has a slight motion. And this is due to the fact that the planet has a very certain amount of mass. And so what we really have going on here is they both orbit around what we call the center of the mass. Now the planet clearly moves much farther, doesn't it? But notice how the star has a very slight motion. So if we were not able to see that planet, but we did see the star making that motion, couldn't we infer that there would be a planet there? I think we could. And that's exactly what astronomers have done. So sometimes you'll hear them use this term, the wobble. The star has a very slight little wobble to it. And this allows us to find the planet. Well, how are we going to measure that motion? Astronomers originally looked for the position of the star to change, but that also was extraordinarily difficult to measure because it's an exceedingly tiny motion. But astronomers are quite resourceful, and they found a little different way to look for that motion, because that's what we're really after, is the motion, not necessarily the position. How are we going to do this? Well, here you see an example. We take the light from the star and we break it into a rainbow, or a spectrum we call it down here. And in that spectrum we're going to see certain lines. In this case, you notice there's some dark lines shown. These lines are indicative of various elements in the star, and that's another interesting field. But what we're going to do here instead is we're going to use those lines to see the star's motion. So the term for this is Doppler shift. The Doppler shift. In other words, if the star is at rest, the lines have a certain specific position in the spectrum. But if the star is moving away from us, those lines all shift towards the red. If the star, on the other hand, maybe is moving towards us, those lines all shift slightly to the blue. Now you might think, well, that's great if it's moving towards or away from us, but think about what we just said. Notice in our little diagram here, if Earth is towards the bottom as the star is moving towards us, won't its light become slightly shifted to the blue? And as the star is moving away from us in this part of its orbit, it will slip slightly to the red. So let me illustrate that as well here by showing you that. Now watch closely. What you're going to see is something that would occur over time. It's not really going to happen quite this quickly. But if the Earth now is over on the left and the star is moving as we saw a minute ago, notice how the spectral line is going to change its position. So this is called the Doppler shift. In other words, the light from the star is very slightly shifted towards the red and towards the blue and towards the red and towards the blue as it moves away from Earth and towards Earth and away from Earth and towards Earth. So this is a very effective and a very precise way to measure the motion of the star from the planet. It tells us there must be a planet there, because the star itself has a motion. So this has become a very powerful tool for astronomers to be able to measure carefully the motion of the star, which again tells us about the orbiting planet. So this technique had been used in the past, but we developed it to a much higher level of precision during the late 1980s, early 1990s, to the level where we could detect a very slight motion of the star, which again would tell us about a planet. So here are some actual observations, some of the early observations back in 1995 of one of the very first planets found around another star, because we noticed the star changing its motion. And if you look at our graph or over a period of a few days, notice we're plotting the velocity here. The star is moving towards us and then away from us and towards us and away from us, just as we described. Below that, you see a few other examples of some of the early discoveries. Now, in our previous animation, you saw the star and the planet both moving around. And if you notice, they were moving around in the same amount of time. In other words, they both circle that center of mass in the same amount of time. And therefore, if we see the star taking a certain amount of time, here in this case 4 days, that's also how long it takes the planet to move around the star. So that gives us the orbital period of the planet. And you may be aware of certain laws. For example, many of you have heard of Kepler's laws of planetary motion. One of Kepler's laws tells us that if we know the period of the orbit, we then know the distance of the planet. So already we're starting to learn a couple of facts about the planet without ever seeing it, because we see the motion of the star. So during the late 1990s, this was a historic time for us to find planets around other stars, to be able to measure their periods, and know how far away they were from their star. Now, these early discoveries, frankly, were shocking. Notice this particular planet takes 4 days to go around its star. How long does Earth take to go around its star? Quite a few more, doesn't it? 365 days. Even our closest planet in our solar system, Mercury, takes about 88 days. So this was quite a shock to say, wow, this planet is orbiting very, very close to its star, much closer than any in our solar system. But frankly, this was just the beginning of some of our surprises as we began to make these discoveries. Well, by the early 2000s, astronomers were attempting another technique, another method, so to speak, and we call this the transit method. Here we have an artist's depiction showing a planet orbiting a star, and if the alignment is just right, if we have a star and a planet circling around it just right from where you sit, the planet could block the light of the star. Now, frankly, the planet is very small compared to the star. It's only going to block a very small amount, perhaps 1%, 2%, something like that. But it's not zero, and we are able to measure it. So once again, one of the very early observations you see down here from 2004 shows that. Each little blue dot is a measurement brightness, and you notice that the brightness here at about 0 dips down for several hours, indicating that a planet is passing in front of the star and blocking its light. So after a few more years, astronomers were able to take this method and turn it into a very effective, very powerful way to also find planets around other stars. And so these are our two main indirect methods that we can find extrasolar planets today. The Doppler shift, or sometimes called the radial velocity method, and the transit method. Here's a little different view, as you can see here. Notice our star, our planet, and I'll put this into animation as well to illustrate exactly how that works. Now, we don't typically see the planet. The planet doesn't really give off its own visible light, but again, if the alignment is just right, notice that the light from the star in green will dip. And here we've greatly enlarged our scale, but if you look closely, you can see it's about 1% of the light that is blocked. Again, a powerful method. In fact, here we can actually get a better idea of the size of the planet by how much light is blocked. In other words, if a small amount is blocked, well, typically that's a small planet. But let me go ahead and change the size of our planet just to exaggerate it. And the point being, if the planet's larger, surely it's going to block more light, is it not? And I think you can see that in our graph. So this immediately tells us a pretty good idea of the size or diameter of the planet without ever seeing it. So throughout our discussion, you'll see both of these methods at work. We'll reference them quite a bit, but these are the ways that we know that there are planets around other stars. Okay, and astronomers have continued to improve and refine these methods. They're very powerful, very effective ways for us to study these stars. So what did we find? Well, the earliest planets detected had very small orbits, very short periods. Why is that? Well, frankly, they're easier to find. It doesn't take as long to find a planet that's close to its star moving quickly as it might be to find one that's farther from its star taking much longer. So we had a little bit of a bias, so to speak, in our early discoveries. We realized, well, we're probably going to find a few more planets at greater distances or longer periods the longer we look. And that's been the case. Okay? One other surprise, though, in this right-hand graph was that many planets turned out to have very elongated orbits, very eccentric orbits. Now, in our solar system, it's true the planets move in elliptical orbits, but they're almost circular. And yet we started to find planets, as you notice here, with greater eccentricity to their orbits. So picture a planet now getting dramatically closer to its star or farther from its star. That was a surprise to us. We began to realize, well, maybe not every planet is like those in our solar system. So slowly, gradually, we were getting a few surprises here as we began to look at other stars and their planets. How about the masses of the planet? Can we get some idea? Well, I'm sure you're aware that mass is related to the gravity of an object. And as a result, think about it, we go back to our diagram. If the star is only moving a very slight amount, you would say, well, the planet's not really that massive, is it? It's not having a big effect on the star. But if the star's moving more, surely that means that the planet must be more massive. And we can tell that, as you notice in our top diagram, by the amplitude of the Doppler shift. In other words, is the star, again, only moving a very small amount, its velocity changes, or is it a large velocity change? This is a clue to tell us how much the star is moving, but that's a clue to tell us how massive the planet is. So you can see, again, we continue to add to what we knew about these planets using indirect methods. So what did we find? Well, most of the early discoveries had large masses. Why? Easier to find. As our earlier technology wasn't quite so sensitive yet, it was easier to find planets with larger mass. They had a greater effect on their star's motion. But over time, we've improved and refined the technology, and we can now find planets with lower and lower and lower masses. So once again, it was a bit of an observational bias. At this point in time, we can find planets basically with masses similar to the Earth, which is a relatively small planet compared to some others. So I think you can see again the resourcefulness of astronomers here in taking some very subtle observations of the stars, but learning about the planets, and then going further and improving that as time goes on. How about size? Well, we mentioned again during the transit how much light is blocked. It tells us the diameter. But think about this for a minute now. If we know now the diameter of the planet, isn't it a simple matter to get the volume of the planet, assuming it's a spherical planet, which nearly all of them are going to be. So we now have volume, and if we have mass, can't we calculate the density? And so now we can begin to learn yet more about the planet. In other words, in our solar system, you know there are the inner planets that are more smaller and denser and rocky, so to speak. And then we have the outermost planets, Jupiter, Saturn, Uranus, Neptune, that are more made out of gas, lower density. Well, once we begin finding the density of those planets, we can start to categorize them, can't we? We can say, well, this must be a rocky planet like Earth, or no, this must be a gaseous planet more like Jupiter. So again, I think you can see that we continue to add more and more to our knowledge of these planets through our observations. So what did we find? Again, one more time. The early discoveries had large sizes. Why? Easier to find, easier to identify with the earlier technology. But again, more recently, we are finding planets more the size of Earth. So steadily, throughout the first decade of the century, we have been adding and improving and gaining in our knowledge of these extrasolar planets. Astronomers continue to tease out more and more information about these objects from various observations of the stars. Can we go any further? What about the composition of them? Well, while we can't tell you the exact composition of the entire planet, we can give you some idea on occasion if it has an atmosphere. Now, if the planet has an atmosphere, and if the planet circles around in front of its star, think about this for a minute. When the planet is not in front of the star, we could easily take not only an image of the star, but a spectrum of the star. And I think I mentioned earlier that we would see various spectral lines indicating the elements that are present. Well, now when we have the planet in front of the star, some of the light from the star will pass through the planet's atmosphere, and that atmosphere will have a subtle but real definite effect on the light. We will see a change in the spectrum. So think about it. You would have the spectrum of the star without the planet and the spectrum of the star with the planet. And if we subtract one out, we would have information about the planet's atmosphere. What gases maybe are present? Perhaps even some idea of the quantity of the different gases or their relative ratio. So again, keep saying a very subtle way to tease out more information about our planet here, the composition of its atmosphere. And as we'll see a little bit later, this leads to yet more questions. Well, if we know that the planet has this atmosphere or these gases, what does that mean about the planet's, again, characteristics? So you can see a very interesting time to be studying extrasolar planets. We've really developed some nice techniques that help us understand so much about these other worlds. Well, you might be thinking that sounds all very interesting and great way to study these, but sooner or later, wouldn't you like a picture? Sooner or later, I'd like to see a planet around another star. Wouldn't that be neat? Here's a few early pictures where it was attempted, and we don't really see a planet. We don't really see a planet. What we see instead is a star that we have actually removed the light of the star, but look what's left over. There's light from the star reflecting off of some disk of particles orbiting around the star. Now in the top picture, we're seeing this flat disk pretty much edge on. In the bottom picture, we're seeing it the other way, really from the top down. So even back in the 1990s, before we had seen any planets, we could see material that they were forming from. So that was a very tantalizing clue that we were getting closer. We were getting closer. And you might think, well, you know, can we again improve our technology, improve our telescopes, our techniques, whatever? And so you think, well, let's use our best telescopes, right? And we often think of maybe the Hubble Space Telescope. So sure enough, astronomers said, let's give it a try. And sure enough, Hubble was successful. Hubble was successful. Here's a close-up picture of a star. Much of the star's light has been removed because it's so tremendously, overwhelmingly bright. But notice this star has a disk of material around it. And close examination showed a little dot of light in 2004 was in this position, 2006 in this position, 2010 and 2000. That object, when we carefully measured its motion, was going around the star. So that's one of our very first pictures of a planet around another star. Doesn't look like much, does it? Very faint, little tiny little dot, but rather profound, wouldn't you say? Rather profound to be able to say, wow, look at that, we actually can see that. We continue to track this object, and as you'll see here, a few others. So again, a very exciting discovery that we could actually now see the planet moving around its star. We also have on the left a false color image. Here we're indicating the intensity of light by the various colors you see. And once again, we've had to remove the light from the star, which is extraordinarily bright. And we once again see kind of an edge-on disk of material here. But when we carefully process the image to carefully remove the star's light, one little dot of light was left over. That's a planet. That's a planet. Okay? So here's another of our few pictures of extrasolar planets. At the bottom right, we see a couple of images that I want to highlight just for a moment. So far, we've probably mostly been thinking about visible light, which you and I are used to seeing, but you probably know that astronomers look at all different wavelengths of light, infrared light, ultraviolet light, and it turns out that in many cases, stars can be quite bright in visible light, but maybe not quite so bright in infrared light. Okay. The point is this still, planets sometimes are the opposite. In other words, in visible light, they don't give off their own light. They merely reflect light from the star, which is exceedingly faint. But if you look closely in infrared light, a planet does give off infrared light. Why? Because it's a longer wavelength type of light that a warm body gives off. A planet's not hot like a star, but it is somewhat warm. You and I are pretty comfortable tonight. So the point being, the right-hand picture, the star's light is somewhat diminished, but the planet's light is somewhat improved, isn't it? And so it makes it easier to see a planet around another star if we look in infrared light. Okay? So slowly, gradually, again, we've continued to improve the techniques, the technology to do that. And here's a few more examples. On the left, if you look closely, we have this exceedingly bright star. And yet look what we have up here. Here's a planet. Here's another example in the center of a relatively small dim star, believe it or not, but a relatively large planet giving off infrared light. And finally, on the right, we have a highly processed image. That's why the star looks so very distorted here. But in this case, we spotted 3 planets. And if you look real closely here to the upper right, you see a little white dot and a red dot. These pictures were taken some time apart. The planet had actually moved. So very dramatic images here of planets around our star. Exceedingly difficult to do, but now barely within our grasp to do that. So really both methods, the indirect method and now the direct method, are in play. Again, direct method, very difficult. We don't have so many of those pictures, but we're slowly accumulating more of those. So what an exciting time to have these techniques at our disposal, to be able to study the planets, again, as we saw with the Doppler method or radial velocity method, the transit method, and we're now able to actually begin to get some images of actual planets. I want to take just a minute and talk a little bit about how planets form. I have a lot written here, but it's important for us to have some idea as we move on in our discussion. So as you can see here, we look out into space and we do actually see enormous clouds of gas and dust. And clearly these clouds with great amounts of matter are going to have gravity. The cloud's going to slowly, gradually contract as the particles are all exerting a gravitational force on each other. And as they do that, it's going to become more and more concentrated or denser in the center. And you can probably guess that sooner or later, as it continues to get hotter and denser, that's going to eventually turn into a star. At first, we call it a protostar before it really fully lights up and provides a lot of energy. But during that time that the star is gradually forming, the gas and dust don't all completely go to the center. Instead, this cloud, as it contracts, will begin to spin a little faster. Some of my students are following me here. We've been talking about this in class. Angular momentum is conserved, and this makes that cloud begin to spin a little faster. It's a little bit like if you were watching the Olympics recently. You saw the ice skaters, right? They'd go into their spin, and some of them would kind of pull their arms in, and they'd spin faster. And as a result, we have something roughly similar here. As the cloud gets smaller in size, it's going to spin faster. Well, spinning faster causes the cloud to flatten. The particles above and below, so to speak, are free to fall inwardly. But the particles perpendicular to the spin axis, they're going to feel a slight outward force, sometimes called a centrifugal force. They're not going to collapse inward quite so much. So essentially our cloud is going to flatten. Well, what does that mean? That means ultimately our protostar will be surrounded by a flat rotating disk. Now that disk surely will not be completely uniform or homogeneous. There will be areas with a little more here, a little more there, and surely the areas a little more material, a little denser. Gravity is going to compress those into planets. So this is admittedly a very simplified version, but I think you get the idea. We call this the nebular theory. As this flattened disk is rotating around the star, the particles are sticking together, getting bigger and bigger and bigger, process we call accretion. And eventually, as the bigger particles merge with the other bigger particles, we're going to end up with planets orbiting our sun, orbiting our star here, in a flat plane. Isn't that what we see in our solar system? We don't see planets flying all over the place. No, they're all orderly in a flat plane, orbiting around their star. Now I want to make one real key point here, as you see in italics. The closer these new young planets are to their star, well, clearly the higher the temperature, right? And so whether the planets were originally made from rock or from ice or gas or dust, whatever, those lighter elements, gas, ice, those kind of things, are going to be vaporized. So the point is that planets closer to the star are going to lose those lighter elements, and they're only going to be remaining rock. On the other hand, planets much farther away are much colder, much lower temperature. They will not lose the gas, the ice type of materials. They will hold on to them. And so very simply in our solar system, we see that, don't we? We see Mercury, Venus, Earth, Mars, smaller rocky bodies near the sun, where it's really too warm for large amounts of gas and ice to exist. But think about it. Out beyond the asteroid belt, Jupiter, Saturn, Uranus, Neptune, much larger planets. Why? Because it's colder, and those planets could hold on to their ice and gas. So we'll see in a few minutes. This is an important point I want to make, but I think it's a very, again, simple, straightforward view of how our planets got where they are today. Okay? So our nebular theory was an excellent first start at understanding our solar system, but we'll see we had to make a few changes over time the more that we learned. Okay? So let's talk about other systems. What are they like? How do they compare? Do they all look like ours? Well, the short answer is no, with a qualified yes. So the first point is that some stars have more than one planet. That's probably not too surprising. We've talked about, a star and a planet, and while that is possible, we have found numerous cases where a star has multiple planets. And again, that's probably not too surprising. Clearly our solar system has multiple planets, doesn't it? Second point you see here is that when we look at some of them, though they're very different, aren't they? Look at the top here where you see Mercury, Venus, Earth, and Mars. Notice some of these other systems, though. Don't they look a little different? Look at how close some of these planets are. So we're going to come back to that in just a minute here. But that's our first clue that something's very different here, isn't it? We don't see them spaced out equally like they are in our solar system. In fact, when astronomers first discovered this, they were so surprised they came up with a new name for some of these planets. Let me back up one slide again. You notice that we have these designated as a certain percentage of the mass of Jupiter. That's what this particular description is talking about. So 0.84 times the mass of Jupiter, 3.8 times the mass of Jupiter. Imagine that, a planet like our Jupiter, or larger, this close to the star? Does that fit with what we just said here? No, something seems wrong, didn't it? What? So we're going to have to discuss this and figure out, well, how can this possibly be? How could there be these huge planets like Jupiter so close to their star? Our nebular theory said they shouldn't be there. Astronomers said, let's call them hot Jupiters. Just a simple name, but it kind of stuck. Some massive planets called hot Jupiters are very close to their stars, but we just said the gas planets shouldn't be that close, should they? They should have been vaporized. So how do you explain that? Astronomers realized that the nebular theory was a good theory, but it was incomplete. It didn't explain this at first, so they had to essentially improve or expand or update that theory. At some point, you have to say, well, the planet simply could not form there with gas and ice. What's it doing there now? There's really only one option, one alternative. The planet had to move orbits. And you and I probably think very much of our solar system completely stable. The planets are where they are. They haven't moved. And while that's not too far off, evidently that's not the case in other solar systems. Let's take a look at some of these others on the right here. You can see a diagram showing various stars and their planets, the size of the red dot indicating the mass. And again, notice, here's Mercury, Venus, Earth, and Mars. Look at all of these systems that have large planets like Jupiter closer than Mars. So even though the nebular theory said, well, they can't form there, it became evident that their orbits must not be permanent. In other words, these planets moved. They formed farther out, and somehow they moved in closer. Now again, we don't normally think of that. Clearly the Earth is not moving in closer. That's good, right? Yeah. We think it's been quite stable for a long, long time. And we see no reason why it's ever going to move out of orbit. But evidently, other planets do move their orbits. So that leads us to the next question. How do you move a planet? How do you move a planet? So astronomers had to go back and think about that and come up with some ideas, and as you know how science works, test those ideas. Maybe our observations would tell us how that might happen. Let's look at two ways that have been brought forward and developed, and we now think are able to explain this. Number one, think about our young star here with the disk of material around it. And as a planet is forming, the planet's going to gain mass. It's going to have gravity. It's going to pull particles in. It's going to basically sweep out a gap in our disk. And no, they're not always green. But the point is it clears out a gap. Now think about this for a minute. If the planet clearly has gravity to clear out the gap, do you think this entire disk has some gravity? Absolutely. This disk is made of countless trillions and trillions and trillions of particles, but they add up. And as a result, this disk has a tremendous amount of gravity, and it can pull on the planet. So if the disk pulls on the planet, clearly there's more material in the disk outside the planet than there is inside the planet. That seems pretty obvious. Well, if you're pulling on the planet, you're going to essentially remove or subtract orbital energy or angular momentum from the planet. The planet's going to slowly migrate inward. See how that works? So if indeed this was a gaseous planet, perhaps forming pretty far out, where it's cold enough for the gas and the ice to survive, but the disk is pulling on the planet, slowing it down, robbing it of energy, it's going to migrate inward. And at some point, we come along and we look and we go, wow, that's strange. What's this big gaseous planet doing close to its star? The disk has caused it to move there. So this is a very plausible, very viable idea that explains how you move a planet inwardly. Okay? We call that planetary migration. Astronomers came up with another idea that also seems quite plausible and very likely. And in this case, it really involves gravitational encounters between planets. So surely stars would form more than a few planets. And if those planets over long periods of time were to get a little close to each other, they would pull on each other with their gravity, wouldn't they? So picture now one planet a little closer to the center than the other, pulling on each other. Well, one of them is going to gain angular momentum, and one of them is going to lose angular momentum. So what does that effectively result in? Well, it means that one planet would move outwardly, but one planet would move inwardly. Now, as I mentioned here in the slide, you move them gradually, but it might also happen fairly quickly. In other words, if for any reason the planets were to come relatively close, there would be a significant amount of energy exchanged here, and they could change orbits relatively quickly. On the other hand, it could also happen very gradually. It might be a very subtle thing that just slowly, periodically, they have some encounters and they exchange orbits. Okay? So this also is a very plausible way to move planets inwardly. Now, interestingly, again, we talk about a gas planet moving inwardly, but I mentioned the other one would move outwardly. If this were to happen relatively quickly, as I said, a significant exchange, the planet moving outwardly could actually gain enough energy to literally leave its solar system, be ejected out into space. And there is now evidence accumulating that this has happened in many cases. And so it's very possible that there are planets that were ejected from their solar systems and they're just sort of floating through space, away from their stars. Sounds kind of lonely, doesn't it? So again, this gives us a very plausible idea of how we move these giant gas planets inwardly. Okay, gravitational encounters. You can see that in our diagram here, that one planet has moved inwardly because of that. So we've had to take our nebular theory and again expand it, enlarge it, improve it, update it. And now that we have these explanations, it's a better theory. It not only explains our solar system, but it explains many, many others. So you can see again the maturing, so to speak, of this field. As we learn more, we add more to the picture of these. So let's go on a bit more now and talk about, so how many are there? Well, here's an astonishing number, I think. Of what we've examined so far, about 50%, about 1/2 of all stars examined have planets. So that's a profound statement that, again, we wondered about for centuries. Now, most of you, I think, know that in our Milky Way galaxy, there's a lot of stars. Billions of stars. And if even only 1/2 of them have planets, well, that turns into billions of planets. So that's quite a thought, isn't it? That's quite a thought. There are so many planets. And frankly, as I mentioned at the outset, our technology is just now getting to the point where we can find Earth-sized planets. There could be smaller ones that we still don't know about, but as a first good estimate, 1/2 of all stars have at least one planet, if not more. There are some stars that don't have any. Sure, we've seen that, and that's another story. But that's quite a profound result here. We've just gotten now enough to statistically be able to say, or make this statement. Okay? Well, in recent years, the focus has turned more to Earth-like planets. It is very interesting to astronomers in particular to study various planets, the large gaseous planets like Jupiter and that, other planets. But sooner or later, most of us are saying, well, could there be planets out there like Earth? That might be very interesting. Oftentimes in science fiction, you see maybe we fly to another star and we want to see the planets. How would we search for Earth-like planets? That's going to be a little tougher than just finding the huge, large gas planets that we've talked about. Well, being such a hot topic, so to speak, or trendy topic, NASA has put great time and effort and money into this search. From the ground, we can look at planets orbiting their stars, and we can figure something out very, very important. You notice in this artist diagram, they're showing, first of all, what's called the Kepler 62 system. And then in the bottom, we see our solar system. Now notice in our solar system, of course, we're all familiar with Mercury and Venus, Earth and Mars. There are various orbits. Now what's this green region? Well, this green region is what we call the habitable zone. I think that word's maybe just a little bit optimistic, but what it really means is the distance from your star, if a planet orbits there, that the temperature would allow liquid water. Okay? The temperature would allow liquid water if you orbit there. Clearly, Earth is well within the green region. Mars, just barely. Venus, oh, it's pretty borderline. Mercury is clearly not. It's too hot there, isn't it? Well, this Kepler 62 system was one of the first that we found that had a planet in the habitable zone. So this was a significant discovery. Now again, I think that, as I said, that word's maybe just a little bit optimistic. It doesn't mean the planet has life, but it has probably the right temperature for liquid water, and most everyone would agree that life requires liquid water. So this got people very interested to say, well, this is close. Sure, we have no evidence of any life, but it might be the right temperature if we were to go visit the system. So this, again, led us to want to look even further, try to find some more systems, try to find one maybe a little bit closer. And this led NASA to propose, develop, build, and launch the Kepler spacecraft. Maybe you've heard of that. The last few years it's been in the news quite a bit because it's been wildly successful. Okay? Kepler was to go out and look for Earth-sized planets in or near the habitable zone, find out, well, how many are there? What's the percentages? Do most stars have one? Do most not? Whatever that case may be. Here's the website if you'd like to go out and see it sometime. So find the percentage of planets in the habitable zone, determine the sizes and shapes of the orbits, that's important. Also the variety of sizes, masses, and densities. And let's also, by the way, take a look at the stars as well, clearly, to understand those stars. Are those stars very much like our sun? Or are they significantly different? So Kepler was designed in a way that really monitored a region of the sky for several years. And its technique, its methodology was the transit method. It was watching very precisely to see if a star dimmed in its light briefly. And then it would continue watching. And hopefully, if there was a planet actually causing the dimming, what would we see? Well, of course, we'd see it do it again, wouldn't we? As the planet circles around the star, it's going to come around, it's going to block the light again. And again. And the minimum acceptable, really, to be reasonably sure you really have a planet would be 3 transits. So Kepler would stare at this region and hopefully see 3 dips in the light, transmit that information down to the ground where it could be analyzed and processed. Now Kepler worked quite well for about 3 years or so. Then it began to have some problems, but they were able to work through those problems and keep the spacecraft running even to this day. What did it find? Look at this graph here. Based on Kepler's data, we now know there are more than 3,500 planets that we have identified. That's a pretty good statistical sample, isn't it? And so you can begin to draw statistical lessons from that. Again, Kepler's data showed that more than 50% of stars have planets. Here's an important fact. 10% of stars appear to have a rocky planet in that habitable zone. So that's a pretty exciting result. You'll say, wow, there are planets out there that would be at least the right temperature. We really don't know much else about the planet maybe yet, but at least temperature, distance from your star, would be something that we could endure. Notice, too, how many more smaller planets there are than the larger ones. So our original observational bias was actually backwards. We began finding the larger ones because they were easier, but clearly there's far more smaller planets than larger ones. Here you see this radius compared to Earth, so Earth would be down here, but you see a tremendous number more than the giant planets. So we're starting to get a statistical way to look at these and get some idea, so to speak, of maybe we'd say the population of planets. Like what kind of planets are out there? primarily smaller ones. It seems that those are a little more likely to form than the very large, massive ones. His graph gives you a little bit idea, not only of the sheer number of Kepler discoveries, but notice from the ground, of course, we can do the transit method. Sure, these blue dots, notice these are brighter stars and these are larger planets. But notice how Kepler is able to show us far smaller planets. In other words, a much smaller dimming of the light. Kepler is extraordinarily sensitive to be able to detect an extremely small dimming of the light, even around fainter stars. So clearly you can see there's plenty of information or data here, so to speak. To this day, Kepler basically sent down 4 major downloads of data, and astronomers continue to sift through it. There's plenty of data still to be analyzed and examined. And essentially, when we find one, astronomers will often zero and say, well, that one looks pretty interesting. That'd be a great candidate for me to go off to a different telescope and examine it more closely. Do the radial velocity method. Watch for more transits. In other words, Kepler's really a survey telescope. It's going out and saying, well, look, here's some candidates. Go ahead and look at these in more detail. And that's exactly what astronomers have been doing, going back and looking at them in more detail. So very, very successful spacecraft. Kind of still working, but having some problems. So we're going to move forward very shortly with additional spacecraft. Here's some examples, just briefly. They're not actually red and green and blue, but you get the idea, okay, of some of the multiple planet systems that Kepler has found. Okay, so interesting to see. Some have larger planets, some mostly smaller. Just a nice sample from the Kepler database of what's out there for astronomers to go examine. Kepler 22b was one specific discovery that got quite a bit of attention. Why? Because it was one of the first smaller planets, so to speak, in the habitable zone that was discovered. When we say small, though, it's about 2.5 times the size of Earth, so it's not exactly a small planet as you and me think. And by the way, what you see there is an artist's impression. It's not an actual picture. So you see it's dramatically or significantly larger than Earth. Recent work, though, going back and looking at this more closely, has established that it most likely is not Earth-like in composition. In fact, as I was looking at this today, the very latest thinking is it probably is more of a gaseous planet. So frankly, this artist's impression was a little bit early, but it's probably not very accurate. We probably don't want to visualize it as a super Earth, so to speak, with a nice friendly atmosphere and oceans. It's probably a little bit more like Neptune, so to speak. Not as big as Jupiter, but still a gas planet. So interesting find. One example of what the Kepler database has shown us. Have you heard of TRAPPIST-1? Yeah, maybe you've heard that. That's been in the news. So just early last year, about a year ago, NASA announced this system with 7 Earth-sized planets in the habitable zone. People got very excited about that. Surely one of them would be friendly, right? Would be hospitable to us. Much of the work here was done with the, as you know, one of my favorites, the venerable Spitzer Space Telescope. Still hard at work, doing great data. Helped us determine the sizes, masses, and densities. And sure enough, they all came out to be small and high-density, rocky planets. So this sounded very promising. And again, this is an artist's impression. But just recently, a closer study was released just a few weeks back that they might actually have some water vapor. Now, of course, if you're closer to the star, you're going to be hotter. That water vapor is in gaseous form. A little bit farther out, it might be cool enough for it to condense into liquid. And a little bit farther out, it might be cold enough it would freeze into ice. Okay, so it's still an early result, but it seems likely that at least some of them could have some water vapor, so that's an interesting discovery. But notice my final bullet here. These stars orbit a very, very small, cool dwarf star. So it's very different from our sun. And there's a couple problems with that if you're looking for somewhere that's going to be hospitable for us. Number one, to stay that warm, well, clearly you have to be very close. You have to orbit very close, and these planets do exactly that. But the problem there becomes 2 things. Number one, small, cool stars like this are known for very energetic flares of energy. Think of them like a giant solar flare. That's not a good thing. But number 2, Think about how the moon orbits the Earth. You know, we look up at the moon every night and we just see one side of the moon, right? And you're probably aware, some of you, that the moon is locked in that type of an orbit. We call it a synchronous orbit, where we only see one side of the moon, don't we? And this gets into the Earth and moon's gravity and so forth. Well, essentially the same thing's happening here. If the planets are orbiting that close to the star, they're going to get locked into that type of orbit as well, where one side of the planet always faces the star. What do you think happens to the temperature on that side? How about the temperature on the other side? So I think you can see that you have to be a little careful here when you say, oh, it's in the habitable zone. That does sound promising, but there are other factors to consider, aren't there? Before you think, well, is it really hospitable to life? Well, maybe, maybe not. Even if some might say, well, you know, maybe it has an atmosphere and the heat can kind of move around. Well, yeah, but when you get extreme heating and extreme cold, you get very strong, fast, powerful winds. So anyway, the point being there's numerous factors to consider before we get too optimistic. But it is a fascinating discovery, and the general consensus among scientists is they feel, well, we're kind of getting closer. We're kind of closing in. And sooner or later, maybe we will find just the right system that looks very friendly, okay, very hospitable for us. So keep your ears open. Discoveries are being made, studies are being done all the time, and it may just be a matter of time before we actually do find a system. Now, can it be numerous factors would have to come into play before we could announce that. So where do we go from here? Well, as I said, Kepler's been working real hard, but frankly, it's having problems, and it's a little bit older spacecraft. Very soon here, NASA will be launching the TESS spacecraft, the Transiting Exoplanet Survey Satellite. TESS is going to take a little different approach than Kepler. TESS is going to focus on nearby bright stars. It's not just going to look at every star it sees, but it's going to really focus on the stars that are closest to the sun, maybe 200,000 of them or so. As it then finds one with transits occurring, astronomers will zero in, they will follow up, they will look more closely at those candidates. So it's kind of like TESS is going to look at the cream of the crop, so to speak. If you want to be studying a system, the closer the better, and that's what TESS is going to go look for here. So this is coming up real soon here. NASA has prepared the spacecraft. The booster's being prepared. By the way, it's going to be launched on a SpaceX Falcon 9. Have you heard about those lately? Yes. So how about that? Okay. Its discoveries will enable us to understand the masses, sizes, densities, orbits, and yes, the atmospheres of some of these planets. Okay, so again, really the nearby brighter stars, easier to study in the follow-up for astronomers. So this should be a real exciting time to see TESS launch. Here's the website if you wanted to go out and have a look at that as well. NASA is looking further down the road. You can kind of see, we of course use ground-based observatories we've talked about. The Hubble Space Telescope you saw, Spitzer's played a very key role, and Kepler. So what's next? Well, TESS, as I just mentioned, and maybe you've heard of the James Webb Space Telescope. This is kind of being billed as the successor to Hubble, and it is loosely, but it's not an exact duplicate of Hubble by any means. It will have other capabilities. James Webb has had some problems as well in its schedule and things, but it's preparing to be launched soon. Soon, we hope. Okay, and there are other things in consideration as well. NASA tends to do what we call a decadal survey every 10 years. They'll put this out to the astronomical community to say, where do you want to spend the money? If we have X amount of money, what do you want to do? Do you want to build another ground-based telescope? Do you want to put a telescope in orbit? Do you want to do this? Do you want to do that? Astronomers will weigh in on that, say, well, we think we as a consensus want to do this. Okay, then let's have some proposals. Let's talk about that. Let's see if we can develop that. So there's always new things, again, that we can look forward to. Even the Europeans are getting in on the game. They're going to be launching a satellite real soon, later this year, to also help us study extrasolar planets. So it's an exciting time. It's an exciting time in this field. We are finding things we never dreamed of 20, 30 years ago, confirming some things, finding new discoveries, as we said. Planets can change orbits, yeah. Just briefly, that forced us to go back and look at our solar system, and while Earth we think has had a very stable orbit, our outer planets appear to have moved since the beginning of the solar system. So that's another kind of interesting story that has implications for our solar system. So lots going on, lots to look forward to. Very exciting time to be studying extrasolar planets. So let's wrap it up with a nice summary, a conclusion. How common are they? We saw that probably half of all stars have at least one planet. Many have more than that. So that's one significant fact. And so if you have 100 billion stars in the Milky Way that are at least somewhat similar to the Sun, you probably have 100 billion planets out there. Number two, how many are like our system? Our system seems very friendly to life. We're here, right? Well, interestingly, only about 25% of systems seem to be similar to ours. So we're somewhat in the minority there. Others, as it says, show clear signs the planets have migrated inwardly and outwardly. Clearly, if you were on a planet moving in or out, that's probably not the most friendly, hospitable place to live, is it? So for those that are very focused on trying to find life on other planets, those are probably not the best place to look, are they? Why the diversity? Well, we were only able to hint briefly at some of the factors again involved, but think about it. As those stars form, those disks form, clearly they're going to be very different. Some stars are going to have more dust, more gas. The disk will be bigger, smaller, thicker, thinner, higher density, lower. There's a numerous number of factors to consider that will have a great effect on what type of planets you end up with. Okay? We saw that there seem to be far more smaller planets. They seem more likely to form than the larger gaseous planets. We happen to have 4 and 4. So the Sun's early disk would have been a certain size, shape, density, temperature, all those things. But other stars are different. I often liken it to people. You know, we're all different. Don't we all have a different story, different history? Started out with different factors that have influenced us, so we end up differently. Same thing, really, with different solar systems out there. Okay? So, again, picture a system where planets are moving around. That's going to have a very different history than our solar system. How about this question? How common are the Earth-like planets in the habitable zone? That seems a very profound one. And the answer, I think, is that we're working on it. But the early data, and I emphasize early, 3,500 stars, about 2% of stars like the Sun, have planets in the habitable zone. Now you say 2% of 100 billion, that's still a lot, isn't it? That's maybe 2 billion planets, and that's true. In our classes, I'm able to go into more detail, and we talk about, well, let's say you start with that number 2 billion. But again, of those, how many of those are going to be disrupted by other planets in the system moving around? We don't know that. So again, keep saying many, many factors come into play before we can really talk about the possibility of life somewhere else. If we take, again, that very limited data, can we get some idea, well, if there was this many, where would the closest one be? This is absolutely just a statistical average. But if it was correct, the nearest habitable planet would be about 50 light years away. Could be 300, could be 12. We don't know that yet. But we're starting to kind of move along and make progress, aren't we, you've seen? Okay? So I'll just finish again, as I mentioned there, many factors influence habitability. We certainly don't have any data right now on life on any other planets. We're kind of at the stage of looking for a, again, hospitable place to look for that. Frankly, we still don't know exactly how life might originate on a planet. I think there's a lot to be done there to understand. But science moves on. We tend to want to keep learning, keep looking, keep searching, don't we? Look how far we've come. Very bright, exciting future ahead of us as we look at these systems. So I hope you've enjoyed our little discussion. Just want to remind you, if you want to see more, come on out to YouTube and find my discussions out there on the stars and galaxies or on the solar system. And I'll close by inviting you back June 23rd. Thank you very much. At this time, I'd be glad to entertain questions. So the question is, we notice the star's motion from the planet. What if there's multiple planets? Don't they all have a pull on the star? And the answer is yes. Each planet will pull a little differently, depending on, of course, several factors: the mass, the distance. And so certainly our star, instead of having a nice simple, well, that marker doesn't work. Some of you know they never do for me. I don't know what.
No magic in that one.
Thus the hands. Instead of having a nice simple motion from one planet out here, let's see if I can do this. You've got multiple planets all pulling differently. The star's going to have a very complicated wobble. You're exactly right. And it takes smart astronomers to go in there and say, well, let's figure this out. There would be a planet out this distance, and there would be a planet here, and there might be one here, and that would explain a very complicated motion. So yeah, we had a very simple example, but you're exactly right. Sometimes in practice, it's a little more complicated. So our next question was, if a planet is ejected from a solar system, flies out through space, first of all, might it encounter another solar system? That's certainly possible, but it's a very, very small likelihood. Why? Because space is so big. That'd be like saying, well, if, I took a rock and threw it out of this room, would it go to a room in Denver? I guess maybe if I have some tremendous... The point is there's so much space between stars, that'd be unlikely. But if it did happen, could it enter another system, I suppose?
What about its own?
On its own. Could it interfere with others? I suppose if it got close enough, yeah. Okay, so that's very possible. Sorry?
What about its own solar system?
About its own solar system? Yeah. If it's ejected, would it affect other planets? Yeah. Absolutely, yeah. If it got close enough to them. If it got close enough. Was there a hand back there? So the question here was about hot Jupiters. In our solar system, our planets are kind of warm and dry. The terrestrial world, so to speak, they're mostly rock. Or they're gaseous and cold out here. And so the question is, well, if you bring this Jupiter planet in closer to the star, what happens to it? Is that the question? What do you think happens? It will gradually be vaporized, yeah. Now that takes time. It's not as quick maybe as you think. We have a few examples, very interesting examples, I'm glad you asked that, of planets where we've monitored their orbits and the orbit is very gradually decaying. In other words, it's getting closer and closer. Why is that? We think it very likely that these planets are being vaporized. There's one system in particular where we have some evidence that this planet is being vaporized and literally streaming like a tail behind it, so to speak. So it might be being vaporized as we watch. Now, clearly, again, this could take thousands, tens of thousands of years, but it is occurring.
Eventually, would it fall into the star?
It is possible that it could fall into the star. It is possible it could migrate in, lose enough mass, possibly attain a stable orbit, but it's very possible it could fall into the star. Again, a lot of factors there.
What would be left behind?
Okay. No, it's a good question. What would be left behind? As you're losing those lighter, we call them volatile elements, ice, gas, that kind of thing, what's left? Just the rock, essentially. Because all planets, even for example Jupiter, Saturn, they do have some rock mixed into them, just they have a lot more gas and ice, so to speak. So if once you lose the gas and ice, and I'm simplifying, what's left? Well, just that little bit of rock. Okay, good question. Yeah, so the comment was, well, currently we can only look out so far within our Milky Way galaxy to studies. That's true. The farther away the stars, the more difficult it becomes. But if we're starting to get our first reasonably good estimate of the number of planets and so on, wouldn't that apply to other galaxies? And the answer would be yes. There's no reason to think it would be any different. So could each galaxy then have billions of planets? Yes. Yeah, there are some other techniques to find planets, some a little more complicated than others. They're still kind of in their infancy, but in time, who knows, that may be able to tell us a little bit more about that as well. So the question was, some of them have elliptical orbits, some planets. How do we know?
Highly elliptical.
Highly elliptical. I took that slide out. I had it in there during the week and I thought, I won't. It's an interesting question. I'm glad you asked it. How do we know? And I don't even have a marker to use, do I? Wait, let's see. So the short answer is, if we see a planet in an orbit that is almost circular, it will have a very uniform type of orbit. Let's go back to, well, here. Okay. We'll have a nice circular orbit. The star's wobble will be very uniform, don't you think? The speed will be pretty much constant. But if a planet gets closer to the star or farther, well, the interaction becomes greater or lesser. So many of you are well aware that as a planet gets closer to a star, or maybe say a comet, what happens? Well, it speeds up, doesn't it? Some of our classes, my class has been studying that. Well, same thing with the star. As the star encounters the planet closer, the star will speed up a little bit. So we would see not a nice symmetrical graph like this, but this graph shape would be distorted. You'd see a much longer, broad shape here, and then it might very quickly change.
When you see in the second graph was
Right down here a little bit. You can kind of get a little bit of a sense of that here. See how this is a much broader curve, and this is a sharper curve? Yeah, so that's a good way to
So
explain.
you get it from the radial velocity?
Yes, the radial velocity. Yeah, I should just go ahead and say that. Yeah, it's not uniform. It's not constant. This very sharp peak here tells us the planet was closer to the star. This very broad one means it's moving slower, and as a result, farther away, yes. Okay, good question. Okay, so the question is, first of all, let me go back. You said the universe is expanding. We learned that because we see galaxies moving away from us. How do we know they're moving away from us? They are redshifted. But the key is an entire galaxy is moving away from us. So the individual stars, it's true, are moving away from us, but the expansion of the universe is of galaxies, and they each have their own stars. We don't see the individual spectrum of that star in a galaxy. They're too far away. Okay, but then you said, well, then we look at a star in our galaxy, and we see it doing this, right? It's coming towards us, away from us, towards us, away from us, yeah. So the point really is, how do we find that? Well, those are much closer to us. Do they have a random motion through space? Yeah, they might be doing this while they're doing this. So it is superimposed. The two are on top of each other. But essentially, one of them is a very steady motion. And we just subtract that out.
Okay.
We just subtract out the nice steady motion of a star through space. We're really just interested in the radial motion. So it's a good question. We want to be clear on. So there's an interesting question. Does every solar system have a belt like our Kuiper belt? Many of you are aware of the Kuiper belt. This is a large number of objects out beyond Neptune, orbiting out there. They're somewhat smaller. And let me just add to that, we think those are probably some of those leftover bodies that never did quite form a large planet. Why? Because out there, there's so much space. They're so far apart. Not a lot of them join together to make a big planet. Okay, so if those are objects that were left over from the formation of our solar system, is that in other solar systems? The answer would be yes. And in fact, we actually got to see basically what you're describing somewhere here. These disks of material could be considered very similar to our Kuiper belt, yes. Okay, what we're really seeing in this picture on the bottom especially, this is actually an infrared picture. It's taken because the particles are absorbing their light from their star. They're heating up just very slightly, and then they're giving off a little bit of infrared light. But these are small particles, and we know that from the various wavelengths. So this would be very similar to our Kuiper belt. Yeah, exactly. Good question. Okay.
Would the wobble in our own sun?
So there's a question. Would our own sun be wobbling? How many would say yes? Absolutely. And it has multiple planets, doesn't it? Clearly, what do you think would have the greatest effect on our sun? Jupiter has the greatest mass. Saturn as well. Earth, Mars, those planets. We are closer, but we're much lower mass. And so as a result, not so much. But technically, if you were to calculate it all out, you'd say, boy, our sun has a very complicated motion, doesn't it? Okay. So they're good questions. Anyone? There's one in the back there? Yes. I did not mention that, but good comment, one of our astronomy club members. I mentioned there's other techniques I didn't have time to go into tonight, something called microlensing, if you want to go home and look that up. If we are fortunate enough that we have a distant star and somehow or other a planet just happens to line up just perfectly with that star, the light from the star can be somewhat magnified. And you and I on Earth, we see a very quick, bright little brightening. We say, oh, that was interesting. Maybe that's a planet passing in front of a star. There is now a paper that's been put out, as you said, that says we think we might have seen that in another galaxy. Someone asked about that. So that would be a way that maybe down the road, who knows, we improve that technique and someday we can look out and see that. So thank you for sharing that, yeah. One in the back there.
I believe you said that not all planets are spherical. What other shapes do they have?
If I did, I apologize. I would say almost all planets are spherical. As a body gets larger and larger and larger, gravity is going to shape it into a sphere. So you should picture just about every planet as spherical. Now there's a few exceptions that we know of. We know of in our solar system it's not a planet, but it is a dwarf planet. And it's rotating so fast that the centrifugal force is elongating it. It's kind of egg-shaped. Okay, so there's always an exception, I guess. Yeah, good. So good question. So the question was, if we observe a system with the transit method or the radial velocity, either method really, and we notice one planet, and how do we notice it? Well, again, we notice the motion of the star. We say, well, that's interesting. The star's moving like this, but maybe there's a subtle little other motion there. We might call it a signature. We can turn that around. Astronomers, mathematicians can turn that backwards and say, well, wait a minute. That little signature, that little motion would be caused by a planet out here at this distance in this orbit. And yes, that's a very productive, viable method that is used. Oftentimes, astronomers will find a system and say, oh, look, there's a planet, great, radial motion or transit, whatever. And then they'll go, oh, wait a minute, let's look a little closer and analyze that. Oh, there must be a second planet. Oh, wait a minute, maybe a third planet. So the TRAPPIST-1 system, they originally found 3. They went back and looked at it and they said, oh, wait a minute. The star's motion is such that there's got to be several more in there. So it's somewhat sophisticated mathematical technique, but you're exactly right. We can go back later and, again, zero in for follow-up and learn a lot more, maybe even find additional planets. And you mentioned orbital resonances. Are those planets, again, affecting each other in some way? Absolutely. Absolutely. We found cases of that where the planets are in such an orbit that you'd say, yeah, they have some influence on each other. So again, a similar question, I think. If we, again, measure the star's motion, we determine the planet, you look at that planet's orbit, and say, might there be another planet? All of the effects are really going to be on the star. Remember, we can only see the star. We can't usually see the planet. It's very, very rarely. We saw 1 or 2 pictures. So it always comes back to the star's motion. Can you untangle multiple planets from it? We're getting a lot better at that. We don't really go to the planet and say, well, let's look at it, because we only know of the planet from the star. But good question. Here's an interesting little tidbit. We're now considering the possibility, let's say that we have, this is kind of related to where you started. You know, you've got this planet growing the star's moving a little bit. Maybe the planet comes in and does the transit, right? Blocks the light. What if the star was coming, or the planet's coming in, and just before the planet gets there, you see a very much smaller little dip in the light, and then the planet dips the light, and then the planet leaves, and then you see another tiny little one. Might there be moons around those planets? Absolutely. So there's been a few papers written on that. On number 1, you know, how do you look for it? What would it look like? How would it? And then can we go do it? We haven't detected one yet, but we've got some data that's getting pretty close. Wouldn't surprise me in the next few years. They say we think we found some exomoons. That'd be kind of neat. What movie was that? So the question is, most of the planets we found have very short periods, and that's exactly true. That's exactly true. I think there was a graph somewhere that showed some of that. And why is that? Well, it takes a long time to track the motion of the star to determine the motion of the planet. So if you have a planet, as you said, out near where Neptune orbits, its motion is very slow. It's going to take a long time for the star to respond to that. We have to watch the star for an extended period of time. Astronomers are impatient sometimes. They want to find the ones where the action's happening, but it is true. The longer we watch a system, the more we maybe find planets farther out because we have a longer time frame that we've watched the star. So that would require patience, and we've done just enough of that to know that there are planets out farther, but not so many researchers spend decades waiting for those longer period planets. But in time, that'll come in time. Yeah. Any other ones? There's yet another one. So the question would be, we saw that in visible light, a planet does not give off light. It's not hot enough to give off visible light. A light bulb is hot enough to give off visible light. You and I don't give off visible light because we're cooler. So then we go to infrared. We say, oh, a planet that is a lower temperature than a star would give off infrared light. The question was, well, can we get to a planet that's hotter to give off light? It would have to be extremely hot. It would have to be as hot as a star or hotter. And planets simply aren't big enough to be that hot. Okay, so no, we're not going to really see a planet give off ultraviolet light. That would require a body that's extremely hot, at least as hot or hotter than a star. It would have to be a star. And for a star to do that, it has to be more massive, yeah. That's a good question, fair question. If there was a solar system pretty darn close to ours, and I don't know, would you say 100 light years away, could we detect it? Absolutely. We can find a Jupiter mass planet. We can even basically find Earth-like planets orbiting a star similar to ours.
And with the Jupiter-like planet, we're not going to have seen enough transits to
That's correct.
detect it yet.
That's correct. So what method would we need to use to find a Jupiter planet around?
Doppler?
Yeah, we'd have to find the radial velocity. And again, we just touched on this. You'd have to be kind of patient and watch it for several years to at least see that star move a little bit. Say, the star's radial velocity is such and such. It moved enough that we know there's a planet there. It would take some time. But yeah, and I think the question was the sensitivity. Are we sensitive to find a system like ours within some distance? Yes, we are. The right system. We'd probably notice the Earth-like planets in closer first, and then if we monitored it long enough, we might say, hey, wait a minute, maybe there's a Jupiter planet out there in a much larger orbit. Very good. Well, again, thank you very much for being with us tonight.